Daytime on 2 continues in just a moment with science topics. This is Daytime on 2. And now we take a look at energy transfer, today's science topic.
450 tons of advanced passenger train, travelling at 200 kilometres per hour. It takes energy to make this happen. But what is energy, and where does it come from? In a steam locomotive, the driving wheels are turned by the force of high-pressure steam, pushing pistons along cylinders. The steam has energy. That energy comes from heating water by burning coal. Like all fuels, coal has energy. It can make things move. This train uses a different fuel, diesel oil. It's burned in engines a bit like those of a lorry. Again, the energy of the fuel makes the train move. The high-speed train also uses diesel oil, but the diesel engine doesn't drive the wheels directly. It turns a generator. That produces electricity, which drives a motor connected to the wheels. But where's the fuel for this locomotive? It's being burnt inside a power station. Under these covers, huge electricity generators are driven by turbines. These blades are turned by the energy of steam, which comes from burning a fuel. The resulting electricity is carried away by the national grid.
You can generate electricity in one place and you can use it in another, sometimes a very long way away. It's very, very versatile. It wouldn't just get very dark on a winter's night without electricity. Electricity can be used for running everything from modern electronics, from computers, right through to heating our homes. It's of unvarying quality and it's nearly always there when we want it. It's also very clean and it's very efficient in its end use.
But a power station can only transfer about a third of the energy of the fuel.
That's not because a modern power station is by its nature inefficient or badly operated. It's because, in fact, there's a fundamental law of nature which tells us that if we try to change energy from heat energy into mechanical energy and therefore into electricity, we can't do much better than that with modern technology. It's the temperature of the steam, essentially, which determines the ultimate efficiency of the power station. And the highest temperature that you can go to with that steam depends on things like materials.
Today, it is vital that we transfer energy with as little loss as possible. Cheap energy disappeared overnight in the price rises of the 1970s, although for the moment, there's no immediate panic.
Something like 80% of our electricity is generated from coal. We've probably got enough coal in this country to last perhaps a couple of hundred years. We have to remember that by the turn of the century, oil and gas will be beginning to run out, and coal will then become too noble a product merely to be burned. We'll be using coal for many things, from for all the things which presently we get from oil, from plastic washing up bowls to aspirins.
At one time, nuclear power was thought to be the answer to the energy crisis. Cheap, abundant, clean, and safe. Nowadays, there is public concern as to whether it can be any of those things.
Well, we believe that nuclear energy is both safe and economic. Therefore, it's something that we would like to proceed with. But of course, we're always on the lookout for other alternatives and other ways of generating electricity. We're very open-minded about other concepts.
It's tempting to think that there must be easy ways of getting energy.
For example, recently somebody suggested that perhaps we should put rollers on roads and motorways, and as cars go over them, we could extract the energy. The problem, of course, is that it's not energy for nothing. Somebody would have to pay for it. The drivers would have to buy more petrol in order to overcome the friction.
In the energy game, you can't get something for nothing. Coal, gas, and oil are rich stores of energy, but they took millions of years to form, and we're using them up in a matter of hundreds of years. They cannot be renewed. But the sun, which helped to make fossil fuels, still shines on the Earth. It's a vast source of renewable energy, but we need new technology to capture and transfer it, such as solar panels, which soak up the sun's energy and make use of the rise in temperature. Or reflectors, which concentrate heat onto a power station boiler to turn steam turbines. And solar cells, which produce electricity directly from sunlight. The sun helps plants grow. Certain fast-growing crops can be harvested and processed into fuel. In a similar way, the sun can be used to split water to make hydrogen, which can be burnt as fuel. The sun is responsible for much of our weather. For instance, it produces clouds and rain. The energy of rainwater running down from high ground to the sea can drive turbines. The sun also produces winds, moving bodies of air with enormous amounts of energy. When winds blow over the sea, powerful waves are produced. So could waves be that large, cheap source of energy we're looking for?
In this country, we're very fortunate because we have a lot of waves off the west coast of Scotland and off Cornwall. Of course, you then have to bring the power quite a long way for it to be used.
At a laboratory near Glasgow, a team is designing what may be Britain's first wave power station.
Waves really only move up and down. Most people think they move along the water, but they're only a vertical movement of the water. Now, by using this motion, this vertical motion, we can then convert the energy of the wave into another form. The simplest way of doing that is to take an object like a tin can. We take the bottom out of it, so it's nice and open, and put a small hole in the top. Then by immersing this in water, say to about this level, if you make a wave outside the water, then the level of water inside will rise and fall. By doing this, it will pump air in and out of the little hole. So we've made a converting machine from wave motion to air motion.
The moving water produces moving air, which in the model pushes up and past a fan. In the real device, the air would turn a turbine to generate electricity.
When the water level rises, we take the air and we push it past the turbine here. By operating valves here and here, when the water level falls again, we can suck air in and pass it across the turbine in the same direction as before and back into the oscillating water column. Therefore, getting a power stroke while the wave is rising and also when it's falling. The sea is a very hostile place, and wave energy devices have to capture the wave energy, catch waves in effect. This means that they have to be very strong and very robust. Our approach was to move into slightly shallower water where the energies were not so great, You could fix the structure to the seabed. It was nearer to the shore, therefore it was more easily accessible for maintenance. By using turbines, which have been around for 100 years, we simply put together well-known engineering concepts in such a way that we could harness wave energy in an economic way.
Somebody once said that they could dream up 10 designs of wave energy devices before breakfast if they had to. And I think that shows the state that the technology is in at the moment. It's at a very early stage.
At Edinburgh University, the duck is one of the few devices to survive the cuts and research funds which the government made in 1979 because wave power looked uneconomic. In the wide tank here, they can accurately simulate the conditions far out at sea, where waves form complex patterns, including the sort of freak wave which only happens once in 50 years.
Well, this is the shape that we call the duck. It's got a cylindrical back, so that as it rotates like that in the water, it doesn't make any new waves behind, and this can make it very efficient. This one here is being tested at the moment, and if you look at the wave height there and compare it with the wave height here, you can see this is much, much calmer. We've got nearly all the energy out. I've got an electrical generator in here which is giving it a force to work against, and I can show you that by unplugging this plug, which will stop the generator sending its energy away, and that'll stop the force. And you can see when I pull that out, the duck suddenly moves a lot more. What we've done is we've taken all the rules that the naval architects worked out for making ships nice and stable, and we've done the very, very opposite.
Unlike the oscillating water column, strings of ducks will float out in deep water.
And this means that the power level is quite a bit higher than it is if you come into areas where the waves are feeling the bottom and losing energy from friction. So we've got perhaps double the power that you might have had otherwise.
Inside the duck, there'll be a complicated system of computers, high-pressure oil motors and gyroscopes, which will produce electricity from the nodding of the duck's beak.
We have never been frightened of complicated technology. We've decided that the best way is to try and guess what the state of technology will be in the late 90s and aim for having ideas ready for what will be available then.
The technology has still got a long way to go. The real difficulty is that you're trying to design devices which will withstand the very worst conditions that the Atlantic Ocean can throw at them. On the other hand, you've got to make them cheap and cost-effective.
As yet, there are no firm plans to build a full-scale station for this country to transfer wave energy to electricity. But whilst wave energy is yet to prove itself, windmills have been in use for hundreds of years. Unfortunately, most of them are now derelict, but a few still run. Windmills used to transfer energy for turning millstones to grind flour or for pumping water. They could do the work of 100 men or a dozen horses in a good wind. But windmills eventually gave way to steam engines and then mains electricity. But now, wind energy is being rediscovered. This is a modern windmill, known as a wind turbine or aerogenerator, for it doesn't grind corn, it generates electricity. The diameter of this rotor is much the same as a large old windmill, but the tower thrusts it high into the air where the wind moves faster and the energy is greater. There are two machines turning on this hillside in the Orkney Islands to the north of the Scottish mainland, one of the windiest sites in Europe. They were completed in 1983, and next to them there'll be a third wind turbine, 3 times as big and 10 times as powerful. In other countries, large machines have been running for years. In 1981, the largest in the world was this American design. It has a rotor diameter of nearly 100 meters, but already larger machines are being built. But size isn't everything. Another approach is to build many much smaller machines, grouped together in wind farms like these in California. Nor must all the designs be the same. There's more than one way of building a wind turbine.
There are two main types of wind turbine machine. This is the familiar horizontal axis machine, which has been around for quite a long time, but this is a modern version, and this spins on a horizontal axis. And then we have the recent developments of vertical axis machines. So these machines rotate around a vertical axis. These are the driving blades, and as you see, it spins like this.
At this laboratory, scientists are experimenting with a small vertical axis wind turbine. One 4 times as large is already being built in Wales. Modern wind turbines have developed from old windmills, but with several improvements in technology. All windmills transfer the energy of a moving body of air into moving machinery. Old windmills turn because the wind tries to push their sails aside. These are wooden sails, but some were frames covered in cloth. Modern wind turbines turn because they have blades shaped like the wings of aircraft.
People wonder why this type of machine turns at all. And in fact, if you consider it in this position with the wind coming across here, then you find that there is no net turning moment. The wind forces on the two blades are equal and cancel. However, if we consider it in this position, which is the best position for turning moment, then we find that the forces known as lift that you find on an aeroplane wing actually develop and cause the machine to turn.
Moreover, these windmills turn whatever the direction of the wind. Horizontal axis windmills only work when correctly lined up with the wind. Then the fantail was invented. It doesn't turn if the windmill is pointing correctly, but if the wind shifts, the fantail starts to rotate and works a mechanism which brings the sails back into the wind. This neat control system is still used on some small modern wind turbines. But for the large machines, sensors which detect wind direction are better. Most windmills need some sort of gears to turn the wheels and axles in the right direction and at the right speed for the job, whether it is grinding flour or generating electricity. Old windmills also have a way of adjusting their sails to let more or less of the air pass through, and so control the speed. Modern wind turbines use a different method.
You want to be able to control the power in any wind. Just this small part of blade, the blade tip, which can change its pitch, enables you to control the power.
Only the blade tips are needed to control the speed of the rotor. Until it is exactly right for synchronizing the generator to the electricity grid. Unlike wave devices, wind turbines are very much up and running now. It's quite clear that the transfer of wind energy has a role to play in generating electricity for Britain.
We're very lucky in this country because by and large we're a very windy country. And we get most of the energy from the wind in the winter. And therefore, there's a relatively large resource, and it comes at the right time. So from that point of view, wind energy looks quite a good bet.
But they still haven't solved all the problems.
The economics have some way to go yet. Manufacturers will have to produce them in very large numbers, rather like they produce motor cars on a production line, to bring the costs down.
And just how many will we need?
Well, to generate 20% of our electricity, for example, from wind power, we'd need thousands of these large wind turbines across the countryside. Everybody loves a windmill, but the windmills of tomorrow's world have blades the length of football pitches, and they soar higher than St. Paul's Cathedral. And the question is, the very large numbers that might be used, would they be acceptable in the landscape?
Would you like a wind farm at the bottom of your garden?